Hello and welcome to this video on spontaneity. Today we're going to take a look at when reactions naturally occur and when they might not naturally occur. And so grab your Cornell notes and let's go ahead and get started. First thing that I think about is just some examples of things that we naturally see occur in all around us. And so here we see that we have a train, and this train was probably made of some sort of iron or metal, likely iron, because what we see on this is rust. And so the question becomes, which thing is going to be the spontaneous process? Going from iron to rust or rust to iron? And what we know is from observation that when we see iron and oxygen, they end up forming iron oxide or rust. And this tends to be our spontaneous process. And it just so happens, if you were to take a look at this, this has a negative delta H. Okay? And so we see that this is going to be an exothermic process. Now, on the other hand, we have some ice over here, and we're going to take a look at this ice. And so we're going from solid water, H2O, solid, and we're actually melting this. And so if you just left this ice cube out, it would melt and it would form liquid water. And it just so happens that this process is actually a positive delta H, and we see that it's endothermic. And so the question becomes, when is it that something is actually going to spontaneously happen? Because we see a spontaneous process that's a negative delta H, and we see one that's a positive delta H. And quite honestly, we can even get, most of our reactions tend to be exothermic, but we do see endothermic ones that naturally occur. And so why is it that something will spontaneously happen? And so that's what we're going to take a look at today. So the first thing we want to know is, when do reactions and processes occur? So when do we see reactions and physical processes happening? Well, they tend to happen when free energy is released. And so what is free energy? Free energy is represented with delta G, or sometimes it's called Gibbs free energy. And it's the energy available to do work. And so this is the energy that's available, still out there for things to be able to utilize. And so spontaneous is naturally occurring processes, and they tend to favor the formation of products. So they go in the direction of products. We'll talk about reversible reactions a little bit later. And so whichever thing they're likely to form tends to be the thing that's going to be favored in that. So if free energy is released, we do see something is going to be spontaneous. Now, that doesn't mean that a reaction won't occur. So sometimes we see non-spontaneous reactions that are coupled with spontaneous reactions in order to allow them to occur. And the most classic example of this is ATP. And so if you remember back to biology, we learned lots about ATP. It's what we make in the process of cellular respiration. And ATP is formed by using the spontaneous process or spontaneous reaction in our cells of cellular respiration. And then it's used, okay, from that harvesting of it, it's actually used to do non-spontaneous reactions by attaching that ATP to whatever enzyme or muscle or whatever it is. And so it's kind of a free energy transfer that allows us to be able to function, first of all, but to get non-spontaneous reactions that are definitely necessary to occur. All right, so that must mean there's some more things out there that we need to know about. And so the next question becomes, what is entropy? And so entropy itself is the measure of the disorder or randomness of a system. And so I think of this with a bedroom. And so I'm sure all of you at home have amazing bedrooms that never get messy. But in my house, we have a little red toy box. So here's our red toy box. And in this toy box, there's all sorts of toys. So we'll just make up some random toys. We'll have a ball here. Maybe there's a doll here. It's got some hair, and there's all sorts of different items that are in here, okay? And so what tends to happen when the kids are playing is it goes from everything being in this nice orderly system here, and it goes towards disorder. So now over here we see the toy box. Maybe we have like one little thing at the bottom that they didn't find, but we have the dolls out here, and we have the ball over here, and maybe whatever. Oh, this is silly putty. We had the dog lay on some silly putty and got it in her. And so there's just stuff everywhere, okay? And so this is disorder. This is stuff moving out, spreading out, being random and all over the place. So this is increasing entropy. Now, in order to go back the other direction, to actually move back towards order, we actually have to add work to it. Okay, so we have to work to get it to be cleaned up again. And so we see that this is actually the spontaneous process. It doesn't feel like much work, more like play, but in order to get this to go back the other direction, it takes us some work in order to do. All right, well, with that in mind, we're going to take a look at some other examples for allowing us to predict if entropy is going to be increasing or decreasing. And so what we see here is that the final entropy is usually, this is going to be our products, and our reactants are initial. If we're working with physical processes, then it's just your before and after, so initials always before. And what we find is that the increasing entropy, okay, the moving towards greater disorder, is a positive delta S because the products have more disorder than the reactants did. And the opposite is the case for decreasing entropy. So remember, this takes some work usually to do. Back there. So it takes us a little bit of work to be able to put that back in order. So let's take a look at some examples of entropy and some different things that we might see chemically and physically. So one of them is temperature and phase change, and we know that increasing molecular motion causes a solid to go to a liquid or a liquid to a gas, and a lot of times we get there from increasing temperature, and that's actually increasing the entropy. So more motion of our particles, more randomness of our particles is going to increase the entropy. And if we decrease the molecular motion, we actually cause these particles to kind of come back together and form something that's more organized and more orderly. If you think about the network solids that we get, where they're going to actually kind of squeeze back together and be more orderly. With gas movement, we see that as things effuse or diffuse, the gas particles expand out, and that's going to be an increase in entropy. But if we compress them, we push them closer together, and that's actually going to be a decrease in entropy. We also see that solution formation, which tends to be very spontaneous. You put something in that's going to dissolve, and it tends to spread out. So that solute will spread out in the solvent, and that tends to be spontaneous, but it also is going to increase the entropy. And then with chemical reactions, we see an increase in entropy as pieces or molecules tend to increase from one side to the other. So as we move across here, what we see is that there's an increase in the molecules, okay? So on this side, I have one, and on the other side, I have these two different ones. I have two particles or two molecules. The opposite is the case for a decrease in entropy, and so in this case here, we see that we're going to decrease the pieces of the molecules. So on this side, we have two, and on the other side we formed one thing. And if you remember back when we took a look at all of our different reaction types, this tends to be decomposition, and this one is synthesis. Okay? And so those are some examples of when we're increasing and decreasing entropy. So keep those in mind. They'll probably show up sometime later as well. So we've talked about entropy, we've talked about enthalpy. Now we want to put this all together. When exactly is a reaction going to be spontaneous or a process going to be spontaneous? Well, it's when free energy is released by the system into the surroundings. And that's when we have negative delta G, or negative free energy. It's actually free energy that's being released. And so we can use this equation. So we have the free energy here. So here's our free energy. And that's going to be equal to enthalpy, or heat, enthalpy, minus the temperature times, so the temperature and the entropy are being multiplied by each other. And so when we see this, we can do some calculations with those values. We just need to remember that temperature will be in Kelvin. And for most processes, or maybe I shouldn't say most, but for many processes, we see they're often spontaneous, and not always, but often spontaneous in the following circumstances. And so one of them is when enthalpy is negative. And so this is going to be our negative delta H. Okay. And we see that oftentimes they are also going to be spontaneous when entropy is positive, because those tend to be the things that happen. Now, that's not always the case, okay? And it's a combination between these two things. And so we really do have to know some numbers. So if this one is negative and this one's quite positive, and then we're going to actually end up with a negative value. But we can see some variation from that. So we really have to plug in some numbers. So let's do that. Let's try an example where we can plug in some numbers. So here's an example of how to calculate free energy. So if a chemical reaction has an enthalpy of negative 81 kilojoules, an entropy of negative 215 joules per Kelvin, is the reaction spontaneous at 50 degrees Celsius? So that temperature, remember, is important as well. So there's a couple things we need to do here. One of them is we first need to get this from Celsius into Kelvin. And so I'm going to take and do my 50 degrees Celsius plus 273 is going to give us a value in Kelvin, and that is going to be 323 Kelvin. So that's the first thing I need to do. Now the other thing, and sometimes you'll be given these two in the same value, and sometimes you will see they're different. So I see 81 kilojoules here, and I see joules per Kelvin here. Well, we need to get them into the same unit, either both into kilojoules or both into joules. It doesn't really matter either way which way you go, but your answer will be represented in the proper one. So let's take that negative 81 kilojoules and make that into joules. So I know for every 1 kilojoule, there are 1,000 joules. Make that a little more legible here. So there are 1,000 joules. And so kilojoules cancels, and that gives us a negative 81,000 joules. Okay, so now I have values that I can plug in. So for delta G, I plug in my negative 81,000 for my delta H, so negative 81,000 joules minus the temperature of 323 Kelvin times the negative 215 joules per Kelvin. So Kelvin's going to cancel, and I'm going to end up with a delta G value, negative 81,000 joules minus, and this number here ends up being negative 69,445, and that's also in joules. And so when I subtract those from each other, I get 11,555 negative joules. And with sig figs, okay, so if I'm going to do this with sig figs, we end up finding out that this is going to be about a negative 12,000 joules. Okay. Now, since this value here is negative, since we see that negative, since it's a negative delta G, it has to be spontaneous. And so that is how we can determine that numerically. We have a few other tools to kind of estimate, but it's really nice to be able to have those numbers in order to be able to predict that specifically. All right, that's all I have for you today.